Special course in mathematics, lecture 6, graph theory. Today we are going to talk about unoriented graphs, and in order to be able to do that, we need to talk about unordered pairs. So let X be a set. Consider the Cartesian square of X, so the set X times X, and this is the set of all ordered pairs of elements in X. So it consists of all pairs X, Y, where X and Y are elements in X. Denote by tilde the equivalence relation on this Cartesian square of X, whose equivalence classes are exactly the singletons X, X, and the subsets consisting of two elements X, Y and Y, X, if X and Y are different. So these equivalence classes are called unordered pairs of elements in X. Let us note that the cardinality of the Cartesian square of X is equal to the square of the cardinality of X, and the cardinality of the set of unordered pair, that is the quotient set of X times X modulo our equivalence relation tilde, is equal to the cardinality of X times the cardinality of X plus 1 divided by 2. So for example, if the original set X consisted of two different elements X and Y, then the Cartesian square of X consists of four elements, namely X, X, Y, Y, X, Y, and Y, X. While the set of unordered pairs of elements in X, that is the quotient of X times X modulo our equivalence relation tilde, consists of three elements: the singleton X, X, the singleton Y, Y, and the set consisting of X, Y and Y, X. Now we can talk about undirected graphs. Definition: a graph, also known as an undirected graph, is a tuple gamma which consists of three things: V, E, and I. So here V is a set, and elements of this set are usually called the vertices of our graph. E is also a set, and the elements of E are usually called edges of our graph. And I is a map from E to the set of all unordered pairs of elements in V. And this is usually called the incidence map. Today we will only talk about finite graphs, so we assume that V is a finite set and also that E is a finite set. So the graphical representation of a graph looks as follows. So we draw vertices as points and edges as lines which connect those vertices. So for example, this picture where we have two vertices 1 and 2 and two edges A between 1 and 2 and B between 2 and 2 corresponds to the following graph. So as a set of vertices we have the set with two elements 1 and 2. As the set of edges we have the set with two elements A and B. The incidence map I is defined as follows. The value of I at the edge A is equal to the unordered pair of 1 and 2, and the value of I at the edge B is equal to the unordered pair consisting of 2 and 2. And a graph without loops and multiple edges is called simple, and in our example we have a graph with a loop, so this is not a simple graph. Now let us talk about connected graphs. Let gamma 1 and gamma 2 be two graphs. So gamma 1 consists of V1, E1 and I1, and gamma 2 consists of V2, E2 and I2. Definition: the disjoint union of gamma 1 and gamma 2 is the graph whose set of vertices is the disjoint union of V1 and V2, whose set of edges is a disjoint union of E1 and E2, and whose incidence map I is a disjoint union of the incidence map I1 and I2. So for example, if gamma 1 is a graph with two vertices 1 and 2 and one edge between them, and gamma 2 is a graph with two vertices 3 and 4 and one edge between them, then their disjoint union has four vertices 1, 2, 3 and 4, an edge between 1 and 2, and an edge between 3 and 4. And a graph gamma is connected, provided that it is not the disjoint union of two non-empty graphs. For example, our graph gamma 1 disjoint union with gamma 2 in this example is not connected, it is disconnected. And here is an example of a connected graph. We have four vertices, 1, 2, 3 and 4, one edge between 1 and 2, one edge between 2 and 3, and one edge between 3 and 4. Alternatively, a graph is connected if we can walk from any vertex of this graph to any other vertex using the edges of the graph. Now let us discuss the notion of a planar graph. Definition: a graph gamma is planar if it can be drawn in R2 without any crossing of the edges. So for example, here is a planar graph. The graph with vertices 1, 2, 3 and 4 and edges between 1 and 2, between 2 and 3 and between 3 and 4. So this simple graph is planar. Another graph which we already saw, two vertices 1 and 2, an edge between 1 and 2 and a loop at 2. That's a planar graph. And here is another non-simple graph, two vertices 1 and 2 and two edges between 1 and 2. These are several examples of planar graphs. And here is an example of a graph which is not planar. So we have vertices 1, 2, 3, 4, 5, 6, and then edges 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, 2, 6, 3, 4, 3, 5, 3, 6. So how it is drawn here, this is obviously not planar, but the question is how to prove rigorously that this graph is not planar. And a couple of next slides will be spent on developing the methods which are necessary to prove that this particular graph cannot be drawn in R3 without crossing of some edges. Our main tool will be the so-called Euler's formula, and in order to formulate it, we need to define the notion of a plane graph. So a plane graph is a fixed drawing of a planar graph in R2 without crossing edges. And of course this is taken up to isotopy in R2. So for example, here are two different plane graphs from the same planar graph. So we have a graph with four vertices, 1, 2, 3 and 4, and three edges, two edges between 1 and 2, and one edge between 3 and 4. This is one way to draw it in a plane. And here's another way. We can place the subgraph of 3 and 4 between the edges of the graph 1 and 2. So these are two different ways, and you cannot change the first way of drawing into the second way without crossing the edges. So each planar graph might correspond to different plane graphs, depending on how we draw a planar graph inside R2. Note that each plane graph divides the plane into connected regions, which are called faces. For example, in both cases above we have two faces. One bounded face is between the edges between 1 and 2, and one unbounded face, which is outside those. And here is the Euler's formula. For any connected plane graph with V vertices, E edges and F faces, we have that V minus E plus F is equal to 2. So let us prove this formula. And in order to do this, we would need the notion of a dual graph. So let gamma be a plane graph. Define the dual graph gamma star as follows. Put one vertex in each face of gamma. Each edge of gamma is adjacent to two faces, and those two faces might coincide, by the way. So we draw an edge in gamma star connecting the corresponding vertices of gamma star for each edge in gamma. So here's an example. So we have the original black graph, that's a triangle. We have 3 vertices and the edges connecting them. So this divides the plane R2 into 2 components. So we have 2 faces, the inner of the triangle and the outer face of the triangle. So the dual graph gamma star has 2 vertices, one for the inner face and one for the outer face. And we have 3 edges, one for each edge of gamma. Note that more or less by definition, gamma star is a plane graph. It comes equipped with a certain drawing of this graph in the plane. Now let us talk about trees. Definition: a tree is a connected graph without cycles. Note that each tree is a simple graph. There are no loops, no multiple edges. Definition: a disjoint union of trees is called a forest. And definition: a spanning tree of a connected graph is a minimal with respect to inclusion connected subgraph on the same set of vertices. Here is an example. The triangle, the full triangle, the graph which consists of 3 vertices and 3 edges between them, has 3 spanning trees. We can leave one edge out. There are 3 ways to do it. So we leave this edge, or this one, or the third one. So this graph has 3 different spanning trees. Also, it is easy to note that the number of vertices of a tree equals 1 plus the number of edges. That's very easy to prove by induction. Now we can prove Euler's formula. Let gamma be a connected plane graph. Let gamma star be its dual graph. Let lambda be a spanning tree for gamma. Then the remaining edges for gamma contribute to a spanning tree lambda star for gamma star. So here is an example which we already saw. So we have our black triangle and then the red dual graph for that triangle. So if we take some spanning tree for the triangle and then we delete the corresponding edges of the dual graph, what remains is a spanning tree for the dual graph. Now for the original graph gamma, we have that the number of vertices in gamma, this is the same as the number of vertices in the spanning tree lambda, minus the number of edges in lambda is equal to 1, because this is true for any tree. And similarly, for the spanning tree lambda star of gamma star, the number of vertices in lambda star, that's the same thing as the number of vertices in gamma star, minus the number of edges in lambda star is equal to 1. If we add these 2 formulas up, we will have that the total number of vertices in gamma, this is V lambda, plus the total number of faces for gamma, which is V lambda star, and minus the total number of edges in gamma, which is E lambda plus E lambda star, is equal to 2. And that's exactly Euler's formula. Here is an application. The graph K33, which we saw before, that's the graph with vertices 1, 2, 3, 4, 5, 6, and edges 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, 2, 6, and 3, 4, 3, 5, and 3, 6. This graph is not planar. Proof. If this graph were planar, then from Euler's formula we would have that for any plane graph associated to K33, the number of faces should be 2 minus the number of vertices plus the number of edges. This is 2 minus 6 plus 9, which is equal to 5. Let us note that each cycle in K33 has lengths at least 4. So if we go from 1, we can go 4, 2, 5, and then back to 1. That's a cycle of length 4. And we cannot do anything smaller than this. Each edge contributes to bounding at most 2 faces. Therefore, to bound 5 faces, which we must have by Euler's formula, we would need at least 5 times 4 divided by 2, 10 edges. But we only have 9. And this contradiction completes the proof. So that's the proof that our graph K33 is not a planar graph. And we use Euler's formula, crucially, to prove this. Here is another interesting consequence from Euler's formula. It guarantees existence of some vertices of small degree. So the number of edges adjacent to some vertex is called the degree of that vertex. So let Vi denote the number of vertices of degree I. Then of course V is the sum over all I from 0 to infinity of Vi's. Here's another corollary of Euler's formula. Each planar simple graph has a vertex of degree at most 5. Of course, to prove this, we may assume that gamma is connected. So assume that the statement of the corollary is wrong. So there is no vertex of degree at most 5. Then V is equal to the sum of Vi's, where I starts with 6. And also 2e, 2 times the number of edges, is equal to the sum of I times Vi, where I starts with 6. That's because each edge connects two vertices. In particular, it follows that 2e minus 6v is greater than or equal to 0. Great. Next, we observe that since gamma is simple, it has no vertices of degree 1, each face has at least 3 edges. So let fi be the number of faces with exactly I edges. Then f is equal to the sum of fi's, where I is greater than or equal to 3. And also then, since each edge is adjacent to 2 faces, then 2e is equal to the sum of I times fi, where I is greater than or equal to 3. Therefore, 2e minus 3f is greater than or equal than 0. So now, combining 2e minus 3f is greater than or equal to 0, and 2e minus 6v is greater than or equal to 0, we have that 6 times e minus v minus f, and this is equal to 2e minus 6v plus 2 times 2e minus 3f. This must be greater than or equal to 0. In particular, it follows that e minus v minus f must be greater than or equal to 0. But this contradicts Euler's formula, which asserts that e minus v minus f is equal to minus 2 for any planar graph. So this completes the proof. Here is yet another local consequence of Euler's formula. Corollary: any simple planar graph with v vertices has at most 3v minus 6 edges. Proof: again, we may assume that the graph is connected, and we have already proved on the previous slides that 2e minus 3f is greater than or equal to 0. Combining this with Euler's formula, we have that 3v minus 6 is equal to 3e minus 3f, and this is greater than or equal than e. Next, let us discuss colorings of the graph. We start with an easy statement, which is called the 6-color theorem. Theorem: vertices of a planar graph without loops can be colored in at most 6 colors, such that no edge connects vertices of the same color. Proof: without loss of generality, we may assume that gamma is a simple graph, because we always can replace gamma by the simple graph when we just combine multiple edges in one edge. Let us do induction by the number of vertices. If the number of vertices is 1, the claim is obvious. Otherwise, we have proved that any plane graph has a vertex of degree at most 5. So let us remove that vertex and all edges which are adjacent to that vertex. The outcome is a plane graph with a smaller number of vertices, so we can color it with 6 colors. And now we can color our additional vertex x into some color which is not used for any of its at most 5 neighbors. And the theorem is proved. So that's a very easy statement. Now let us prove the so-called five-color theorem. Theorem: vertices of a planar graph without loops can be colored in at most 5 colors, such that no edge connects vertices of the same color. Proof: similarly to the previous theorem, we may assume that gamma is a simple graph. Let us assume that the assertion is wrong. Let gamma be a connected planar simple graph on V vertices that cannot be 5-colored. And we can assume that V is a minimal possible number with this property. So if we delete one vertex, we can always 5-color the outcome. Let X be a vertex of gamma of minimal degree. We know that this degree is at most 5. If the degree were at most 4, then exactly the same arguments as in the previous proof, in the proof of the 6-color theorem, give us 5 coloring for gamma. So this is not possible. This means that the degree of X is exactly 5. Now let us look at the 5 neighbors of X, and they must be colored in 5 different colors, because otherwise we can do the same argument as before. So we have our vertex X here equal to V on this picture. It has 5 neighbors, and they all have 5 different colors, as on the picture. So let us look at the colors 1 and 3, and let us look at the connected subgraphs, which starts from this vertex of color 1 and only has colors 1 and 3. Starting from the neighbor of X, which is colored with color 1, and starting from the vertex of X, which is colored with color 3. There are 2 cases. First case, that this subgraph is not connected. We cannot come from this vertex to this vertex by changing colors. If this is not connected, we can swap color 1 and 3 in one of these connected components, and now we have the situation when the 5 neighbors of our vertex X are colored in 4 different colors. So we can color the vertex X in the remaining 5th color. And we are done. So this case is not possible. Now the case which is possible is that the graph for the vertices with colors 1 and 3 between them is connected. But if this graph is connected, we can look at the graph for colors 2 and 4, and then that graph must be disconnected because our graph is plane. It's a planar graph, so we have a connected version starting from X and going color 1, 3, and so on, 3. And now the vertex V2 is inside this component and V4 is outside. So that graph is disconnected, so we can apply the previous argument by swapping the colors 2 and 4 in one of these connected components, and then get an admissible 5 coloring of the original graph. And this completes the proof of the 5-color theorem. Now some remarks about the 4-color theorem. This is one of the most famous theorems in mathematics. So theorem: vertices of the planar graph without loops can be colored in at most 4 different colors, such that no edge connects vertices of the same color. Originally this was proved by Kenneth Apel and Wolfgang Haken in 1976, and the proof uses quite significant computer-assisted colorings of some small, so to say, graphs. And a simpler proof was published in 1997 by Robertson, Sanders, Seymour, and Thomas. Still, this simpler proof uses computer computations, and some skeptics remain as for whether one should accept proofs which use computer assistance. And for details, one can check the Wikipedia page for the 4-color theorem. How about 3 colorings? It is very easy to see that there is no 3-color theorem for planar graphs. If you simply consider the full graph on 4 vertices, this is obviously planar. So here is a plane graph, which is a full graph on 4 vertices, and this is obviously not 3-colorable because each vertex is connected to 3 other vertices. So the 4 is the minimal number of colors needed to color admissibly all planar graphs. Thank you very much, and this completes this part of the course.